Hello and welcome to very special episode on crystallography and mineralogy. I am Ashima teaching in the Department of Geology, University of Delhi. Students, first we will talk about phyllosilicates. Sheath silicate minerals are known to be important and abundant in all rock types, be it igneous, metamorphic or sedimentary. In terms of geologic environment, they are stable at or within about 20 kilometers of the earth's surface. They are of hydrous nature and the hydrogen is usually bonded to oxygen to form OH group. Commonly are known as phyllosilicates based on the Greek derived term phylon, meaning leaf owing to its flaky habits. Many prefer to call them as layer silicates as well. The structure of sheath silicates consists of two different sheaths, O octahedral sheaths and T tetrahedral sheaths. Octahedral and tetrahedral sheaths are joined together to form layers and are stacked on top of one another and bonded to form the repeating unit of the mineral. The gap between the two layers is usually filled by interlayer cations and or water or may remain vacant as well. As the bonding between the two layers is weak, it gives the sheath silicates the diagnostic single perfect cleavage. The octahedral sheaths typically consist of two planes of OH anionic groups. Divalent cations such as Fe2 plus and Mg2 plus or trivalent cations such as aluminum 3 plus and iron 3 plus occupies the octahedral sites formed between the OH anionic groups. Based on this, if the cations are divalent, 3 out of 3 octahedral sites gets filled, forming trioctahedral sheath. Likewise, if the cations are trivalent only, 2 of the 3 octahedral sites are occupied due to charge balance requirement, resulting in dioctahedral sheaths. The net charge on both dioctahedral and trioctahedral sheaths is 0, the net cation charge being +6 in both the cases. Site occupancy has a direct bearing on the unit cell size. Hence, in the dioctahedral sheath silicates, the B unit cell dimension is about 9 angstrom, whereas in the trioctahedral sheaths, B unit cell dimension is about 9.2 angstrom. Tetrahedral sheaths consist of sheaths of tetrahedrali coordinated cations whose compositions can be represented by the general formula T2O5, where T represents cations, usually Si4 plus, aluminum 3 plus or less commonly Fe3 plus. The tetrahedra are arranged in a mass of 6-fold rings with 3 O2s on each tetrahedra get shared with the adjacent tetrahedra and are known as basal oxygens. The fourth unshared oxygen is known as the apical oxygen. So, a tetrahedral sheath has the chemical formula Si2O5 with a 2 negative charge. Sometimes Al3 plus and Fe3 plus substitutes for Si4 positive, increasing the net negative charge on the tetrahedral sheath. The unbounded tetrahedral apices of the sheath all point in the same direction. These apices connect the tetrahedral sheath. The apical oxygen atoms of the tetrahedra shared with an oxygen atom or the OH anion from the octahedral sheath. Different stacking combinations of the two connected basic tetrahedral and octahedral sheath results in the phyllosilicate structures. Now, we will discuss the structure and classification of the phyllosilicates. The phyllosilicates are classified by the way in which the layers are built up of tetrahedral and octahedral sheaths and by the way they are stacked relative to each other. 3 main groups of layer silicates are known to occur. Number 1, we have in the 1:1 the layers are made up from one sheet of SiO4 tetrahedra combined with one octahedral sheet. These layers are charge balanced and weak bonds are known to hold successive layers together in the stack. In the 2:1 phyllosilicates, the second category, an octahedral sheet is sandwiched between the apices of two tetrahedral sheets. The tetrahedral, octahedral, tetrahedral layers are held together by weak van der Waals force if they are neutral, or may have cations between them if substitutions in either of these sheets results residual charge. In the third category, in the 2:1:1 layer silicates, an additional octahedral sheet is found sandwiched between each TOT layer. 1:1 phyllosilicates, we will discuss it in detail now. The combination can be represented as below from a dioctahedral TO layer. We have one layer of T silicates plus one layer of O silicates resulting in a TO layer, and in between we have the hydroxyl group. The equivalent trioctahedral TO layer is Mg3Si2O5OH4. Example of dioctahedral variety is Kaolinite, and that of trioctahedral variety is Serpentinite. All the 1:1 layer silicates are soft as the bonding between the layers are of weak electrostatic nature. The repeat distance from one layer to the other is about 7 angstrom, and so the unit cell dimension is either about 7 or 14 angstrom depending on the number of layers in the structure. Now we have the 2:1 phyllosilicates. The 2:1 layer silicates are constructed of repeating TOT layers. Depending on whether the TOT layers have a net negative charge and what is placed between the interlayer sites decides the varieties of 2:1 layer silicates we will have. The first variety of 2:1 layer silicates is with no interlayer sites. In the general 2:1 layer silicates, the dioctahedral and trioctahedral TOT layers are electrically neutral. The bonding between the adjacent layers is also weak, van der Waals and hydrogen bonds. Talc represents the trioctahedral variety and pyrophyllite represents the dioctahedral variety of phyllosilicates from this group. Weak interlayer bonding results in the soft waxy feel of both talc and pyrophyllite. The repeat distance between the layers are between 9 and 9.5 angstrom or multiple of it, depending on the number of layers we have in the unit cell. The second variety of 2:1 layer silicates is one with cations like potassium in interlayer sites. The structure consists of TOT layers wherein some tetrahedral sites are occupied by alumina Al3 plus rather than Si4 plus. Common minerals which are included in this group are Micas and the brittle Micas. In the Micas, the ratio of Al3 plus to Si4 plus in the tetrahedral site is 1:3. In the dioctahedral TOT layer, the general formula is Al2, AlSi3O10, OH21, and for the trioctahedral layer, TOT layer, the general formula is Mg3, Al, Si3O10, OH21. The net negative charge of these layers is balanced by inserting monovalent cations such as potassium between the layers to form muscovite in case of dioctahedral variety, and phlogopite is the trioctahedral equivalent of this. The interlayer cations that are situated in the centers of the tetrahedral rings in the centers of the tetrahedral sheets. The repeat distance between the layers are slightly increased due to the addition of interlayer cations to 9.5 to 10 angstrom than for the TOT structure. As both ionic and van der Waals bonds are involved to bind the adjacent TOT layers and the interlayer cations, micas show a hardness between 2 and 3. For the brittle micas, structure is same except that more tetrahedral are occupied by Al3+. In the dioctahedral mica margarite, half of the tetrahedral sites are occupied by Al3+, so the TOT layers are Al2, Si2, O10, OH22. The net negative charge of 2 is balanced by insertion of calcium 2+ in the interlayer site. The trioctahedral variety of brittle mica is known as clintonite with a formula of CaMg3 Al, AlSi Al3, SiO10, OH2. In this structure, 1/3 of the octahedral sites contain Al3+, the excess charge being balanced by the substitution of additional Al3+ for Si4+ in the tetrahedral site. Now, we have the third category of interlayer silicates. We have 2:1:1 phyllosilicates. This structure can be derived by adding an octahedral sheet between the TOT layers. The most common representative of this group is chlorite group of minerals. You have a talc-like layer which you combine with a brucite-like layer to give rise to a chlorite unit structure. Chemically, it is Mg3 Si4 O10 OH2 combined with Mg3 OH6 giving rise to Mg3 Si4 O10 OH2 Mg3 OH whole 6, which is the chlorite mineral. The repeat distance of the unit cell is about 14 angstrom. The Al3+ substitutes for about 1/3 of the Si4+ in the tetrahedral site. This gives the TOT layers a net negative charge. However, the internal interlayer octahedral sheet has a positive charge produced by substitution of Al3+ and Fe3+ for octahedrally coordinated divalent cations. The net negative charge on the TOT layer is balanced by the net positive charge or the interlayer O sheet. Then now we will discuss about the tetrahedral octahedral mismatch in the layer silicates. In the dioctahedral kaolinite structure, aluminum occupies 2/3 of the octahedral sites, which results in the mass size of the aluminum octahedral sheet being smaller than that of the tetrahedral sheet. A better fit is achieved when these SiO4 tetrahedra rotate by about 9 degree about an axis normal to the sheet with adjacent tetrahedral rotating in opposite senses. In other types of 1:1 phyllosilicates, the degree of mismatch depends on the cations occupying the tetrahedral and the octahedral layers. The rotation of the tetrahedra needed to link the two sheets increases by replacement of Si4 positive by the smaller Al3 positive ion in the tetrahedral layer and decreases by replacing the Al3+ ion by the larger Mg2+ ion in the octahedral layer. This type of mismatch is well exemplified by 3 forms of minerals of serpentine family, namely lizardite, chrysotile and antigorite. Each of these reflect a different attempt at coping with this tetrahedral octahedral mismatch. In the 2:1 phyllosilicates, curvature of the layers on any microscopic scale is not seen. However, in talc, this feat is achieved by a tetrahedral rotation of about 3.5 degree, and in pyrophyllite the tetrahedral rotation is about 10 degrees. In cases where the octahedral sheet is too large for the tetrahedral sheet, it gets more difficult to stretch the tetrahedral sheet to fit in. In such cases, the octahedral sheet has to split into ribbons to reduce the strain, as we see in minerals such as sapiolite and palygorkisite. Now we will discuss the representative minerals belonging to the phyllosilicates. The first group is the kaolinite group. We will first discuss the structure and composition of the kaolinite group. It is a type of dioctahedral clay with a 1:1 layer with no interlayer cation and a composition of Al2, Si2O5, OH4. Dikite, halloysite and necrite are polymorphs of it. Now we will discuss the crystallographic properties of the kaolinite group. It belongs to triclinic system, point group is 1 and space group is P1. The unit cell parameters are A is 5.5 angstrom, B is 8.95 angstrom and C is equal to 7.39 angstrom, and the alpha angle is 9.18 degree, beta is 104.5 to 105 degree and gamma equals to 90 degree and Z is equal to 2. Now we will list the physical properties. Usually kaolinite group minerals are white to tan colored, but may be variously colored due to presence of impurities. Rarely they occur as crystals, thin, platy or stacked to 2 millimeter is how they occur. More commonly occur as microscopic pseudo-hexagonal plates and cluster of plates. Cleavage is perfect on 001 phase. Hardness varies from 2 to 2.5. Specific gravity varies between 2.61 to 2.68. It gives a streak of white color and is non-pleochroic. Luster varies from pearly to dull earthy. If we go to the optical properties, minerals belonging to kaolinite group in thin sections appear as fine grained brown to gray earthy aggregates. It is biaxial negative in character. Optic orientation is the angle between X and C crystallographic direction is -13 degree to -10 degree. The angle between Y and A is 1 to 4 degree. N alpha varies from 1.503 to 1.563. N beta is equal to 1.559 and N gamma is equal to 1.560 to 1.570. The 2V angle varies from 24 degree to 50 degrees, are known to have low to moderate positive relief in thin section. As for their occurrence, we find them associated with quartz, feldspar and muscovite. They all primarily form by weathering or hydrothermal alteration of feldspars. It is also a common constituent of the clay size fractions of sediments, where it forms by direct precipitation. Kaolinite group of minerals are used as drilling mud additive, used for ceramics, as filler materials, are finds used in cosmetics, used in refractory and building products, are also used in manufacture of Portland cement and are used as absorbents and also finds use in pharmaceuticals. Serpentine group is another mineral group belonging to phyllosilicates. We will first discuss its structure and composition. All the three varieties of serpentine group of minerals have a composition of Mg3, Si2, O5, OH4 and are named as chrysotile, lizardite and antigorite. They are all trioctahedral 1:1 layer phyllosilicates. The lateral dimensions of the tetrahedral and octahedral layers in an ideal 1:1 layer are different, which results in a misfit, which we have already discussed. The three varieties of serpentine minerals results due to different attempts at coping with this tetrahedral octahedral misfit. In lizardite, the tetrahedral rotation is around 3.5 degree. In chrysotile, the tetrahedral are slightly tilted so that their apices no longer lie on a flat plane. The increased distance between the apices to achieve a fit with the octahedral mesh results in curvature of the whole layer. Continued growth of crystal results in rolled up layers. In the antigorite variety, the curvature of the layers is accompanied by periodic switching of the direction of the tetrahedral layer. Mostly are close to the ideal composition, but substitution of aluminum 3 plus for Si4 plus or Al3 plus, Fe3 plus or Fe2 plus for Mg2 plus may occur. As for the crystallographic properties of serpentine group of minerals, chrysotile is orthorhombic or monoclinic, lizardite is hexagonal or monoclinic, and antigorite belongs to monoclinic crystal system. Point group is 2m, space group is p bar 31m. Lizardite has a unit cell parameter of A equivalent to 5.3 angstrom and C is about 7.25 angstrom. Antigorite has a unit cell parameter A of 3.33 to 51 angstrom, B of 9.25 angstrom and C about 7.25 angstrom. The beta angle is 91.4 degree. Chrysotile has a unit cell parameter of A equivalent to 5.3 angstrom, B equivalent to 9.25 angstrom, C equivalent to 14.6 angstrom. The beta angle varies between 93.3 or 90 degree. As for the physical properties of serpentine group of minerals, they usually occur in shades of green, yellowish green, white or gray. Generally gives a white streak, are silky, greasy or waxy in luster, shows perfect cleavage on 001 phase. Chrysotile is known to form fibers, lizardite occurs as fine grained masses, whereas antigorite can form scaly or foliated masses. Twins are uncommon in serpentine, may show weak pleochroism in rare cases. As for the physical properties, lizardite is known to show a density of about 2.55, hardness of 2.5. Antigorite has a density of about 2.6 and the hardness varies from 2.5 to 3.5. Chrysotile has a density of about 2.55 and hardness varies from 2 to 2.5. As for the optical properties of minerals belonging to serpentine group of minerals, they show colorless or pale green or yellow green color in thin sections, shows moderate relief and are biaxial negative. We have the N alpha varying between 1.529 to 1.595, N beta varying from 1.530 to 1.603 and N gamma is equal to 1.537 to 1.604. We have the 2V angle varying between 20 to 50 degrees. Optic orientation, alpha is parallel to Z, gamma is equal to Y. Occurrence of serpentine group of minerals. Usually they form by hydrothermal alteration of mafic and ultramafic rocks. Chrysotile is stable at less than 260 degrees Celsius, whereas the antigorite variety of serpentine is stable up to more than 600 degrees Celsius. The associated minerals with serpentine group of minerals include calcite, we have brucite, chlorite, magnetite and chromite. They are also found to occur in association with calcite, dolomite, forsterite, magnesite and calc silicate minerals in contact metamorphosed carbonate rocks. The serpentine rich rock is known as serpentinite, which is commonly found in subduction zones. Where do the serpentine group of minerals finds use? Low thermal conductivity and incombustibility makes it a valuable industrial mineral. Mostly find use as asbestos and also finds use in automobile industry as brake shoe and clutch facings. It is also used in fireproof insulators and in construction materials. Another group of mineral belonging to the phyllosilicates is the talc. We will first discuss the structure and composition of the talc. It is a trioctahedral 2:1 layer silicate with a composition of Mg3, Si4, O10, OH2. The composition is usually close to the ideal formula, though minor substitution of iron, manganese or other cations for magnesium in the octahedral sites and aluminum for silicon in the tetrahedral site is known to occur. Iron bearing variety of talc, minnesotite, which has a composition of Fe3, Si4, O10, OH2 is commonly found in metamorphic iron formations. As for the crystallographic properties of talc, it belongs to triclinic or monoclinic crystal class. Point group is 1 bar, 1 or 2m. Space group is C 1 bar or C 2 by C. Unit cell parameters are A is equal to 5.290 angstrom, B equal to 9.173 angstrom and C is equal to 9.460 angstrom. The alpha angle is about 90.46 degree, beta is 98.68, gamma is 90.09 and Z is equal to 4. The physical properties of talc usually shows white, light to dark green or brown color. It occurs as foliated, radiating or randomly oriented aggregates of irregular flakes or fibers. Talc has a soapy feel and is sectile. Cleavage is perfect on 001 phase, is known to give a white streak and shows pearly luster. It shows no pleochroism and twinning. Hardness is diagnostic 1 and specific gravity varies from 2.58 to 2.83. Coming to the optical properties of talc, in thin section it appears colorless with a low to moderate positive relief, is biaxial negative in nature. The N alpha varies from 1.538 to 1.554, N beta equals to 1.575 to 1.599, N gamma equals 1.575 to 1.602. The 2V angle varies from 0 to 30 degree. The optic orientation is that the angle between X and C crystallographic direction is plus 10 degree, Y is equal to B and Z direction is equal to A and optic plane is oriented along the 0, 1, 0 phase. As for the occurrence of talc, it is commonly found in metamorphic environment, formed due to metamorphism of siliceous dolomite, where it is found associated with calcite, dolomite, tremolite and other calcilicate minerals. Talc also forms due to metamorphism of mafic igneous rocks or mafic volcaniclastic sedimentary rocks associated with magnetite, tremolite, chlorite, anthophyllite or serpentine. Talc is also commonly found in hydrothermally altered mafic and ultramafic rocks in association with serpentine, magnesite and relict grains of olivine and pyroxene. As to where talc finds use in industry, it is used as a filler and colorant in paint, rubber, etc., and as a lubricant. It finds widespread use in cosmetic products as well. Moving on to another group of phyllosilicate, that is the pyrophyllite. We will first discuss the structure and composition. It is a dioctahedral layer silicate and consists of two TOT layers in monoclinic unit cell and one layer TOT in the triclinic polytype. The ideal composition is Al2 Si4O10 OH2. Common substitutions are Al3 plus for Si4 plus and Mg2 plus, Fe2 plus and Fe3 plus or Ti4 plus for Al3 plus. Minor substitutions of calcium, sodium or potassium may be present in interlayer cations. Coming to the crystallographic properties of pyrophyllite, it crystallizes in both monoclinic and triclinic crystal system. Point group is 2 by M and 1 bar. Space group is C 2 by C or C 1 bar. Cell parameters for monoclinic unit cell is A is equivalent to 5.17 angstrom, B is equivalent to 8.96 angstrom and C is equivalent to 18.68 angstrom. The parameters for triclinic unit cell is A is equivalent to 5.16 angstrom, B is equal to 8.96 angstrom, C is equal to 9.35 angstrom. The alpha angle is about 91 degree, beta angle is about 100 degree and gamma is also about 90 degree and Z is equal to 2. We will discuss the physical properties of pyrophyllite. It occurs as foliated, columnar, radiating masses or as massive aggregates. It also shows fibrous habit, has a dull to pearly luster. It is usually of white, pale blue or brownish green color. It gives a white streak. It shows no twinning and is sectile. Is known to show perfect cleavage on 001 crystallographic phase. Hardness varies from 1 to 2. Specific gravity varies from 2.65 to 2.90. As for the optical properties of pyrophyllite, it is colorless in thin section. It shows low to moderate positive relief, is biaxial negative, has an N alpha of 1.552 to 1.556, N beta is equal to 1.586 to 1.589. N gamma is equal to 1.596 to 1.601. The 2V angle varies from 53 to 62 degree. Optic orientation wise, the angle between X and C crystallographic direction is 10 degree, Y is equal to A and Z is equal to B. As for the occurrence of pyrophyllite, it is usually found in low grade aluminum rich metapylites, metabauxite or metaquartzite formed due to hydrothermal alteration of aluminous minerals such as feldspars, muscovite and aluminum silicates. As for the use of pyrophyllite, it finds most common use as refractory line in kilns, furnaces and ladles in foundries. also used in ceramic industry as filler in paints, cements and as construction material.